superposition question from exam 1. Consider a negative point particle with charge negative q held fixed at location C, 0L0, L is greater than 0. A permanent dipole P is held fixed at location B, L00, L is greater than 0. Using your cell phone, you measure the net electric field at the origin and find it to be equal to 0. For all the parts of this problem, you can assume that the distance from the dipole is much larger than the size of the dipole, i.e. S is less than L. The first part of the question is to determine the dipole moment, magnitude, and direction of the permanent dipole in terms of Q, L, and other fundamental constants. So first, I drew out the scenario and indicated the net electric fields at the origin. E net is 0 at the origin, and so given that the dipole moment is creating a perpendicular dipole for the electric field at the origin, and E net should be equal to 0, E net being E negative plus ED perp at the origin, then we can determine that ED perp should be equal to negative E field for the electron. At that point, you can also determine that R hat for the negative particle is equal to negative Y hat, which should be equal to L, which was given earlier, such that L can now be used as R in the equation to determine an electric field. So, given ED is equal to negative E negative electron, negative E negative electron looks like ED equal to negative E negative electron equal to a negative, in parentheses, negative KQ over L squared times negative Y hat. This can then be translated into simply negative KQ over L squared times Y hat as those signs cancel out. So now that we see ED perp hat is equal to negative Y hat, we look at the dipole on an axis perpendicular to X hat. Given that S is less than L, we use the approximation for an E field without S. This means ED is equal to ED perp, and negative Kp divided by R cubed can also be translated to L cubed from our earlier consultation. L cubed is also equal to L squared, 1 over L squared times Y hat here. And so you'll see that when we set the equations of each E field equal to one another and cancel out a lot of the constants, the dipole moment is actually equal to QL times Y hat. So then you translate that into a vector, and it's 0, QL, 0. So that's the dipole moment. The next part of the question is asking, without moving the permanent dipole, you accidentally rotate it so that the dipole moment points in the positive X direction. Determine a location A where you would place a positive point particle plus Q so that the net electric field at the origin is once again 0. So we're going to redraw our original photo. Here you'll see the dipole is now parallel to the origin. And so we're trying to determine where's a place where we can place particle A such that E net at the origin is again 0. So we'll start with the dipole moment. This is now equal to QL x hat. So in the vector format, that's QL comma 0 comma 0. And we want E net to be equal to ED plus E negative plus EA, which should be equal to 0. So at this point, we can determine that EA should be equal to negative parentheses ED plus E negative. So now that the dipole is on axis, the E field for the ED changes from the perpendicular dipole formula to the parallel dipole formula to the origin. S is still less than L. So here you'll see the math done for the electric field of A, where we're now inputting negative parentheses ED plus E negative, those formulas, and then working out and canceling some of the variables here. We then add in the magnitude, which is the square root of 5, and factor that out. So you're multiplying everything times root 5 over root 5. And then you'll see here, we have KQ L squared times root 5 times the vector negative 2 over root 5, comma negative 1 over root 5, comma 0. So EA is equal to KQ over R squared times R hat. And we equate the magnitude and direction of both sides here. Then you'll see that R is equal to L over 5 to 1/4. And if we want the vector R, what we needed to do is multiply that R that we just got times R hat being found here for negative 2 over root 5, negative 1 over root 5, 0. And so our vector can be seen here for where we'd want to place EA. And we find that it is the relative position. And so to determine RA, we want to give R observation times R, which would be 0 minus R. So given that we just solved for the relative position, and we want RA, we then multiply these here, and eventually just get, because of 5 to the fourth being sorted here, we'll get L times 0.6, 0.30. So this is the relative position, or this is the RA vector for the place where we'd want to put the proton to balance out all of the E fields so that at the origin E net is equal to 0. With this problem, you'll say that the basic principles covered are dipoles, parallel and perpendicular dipole fields, dipole moments, and dipole superposition. We also get into electric fields and position vectors. If we want to build on those basics and test our general understanding of this problem after working through, we could work with different point charges, protons instead of electrons, and vice versa for both the original set and the modified set in part B. And this will help us to ensure that we understand the signs and the dipole positioning itself. We could also include S as a significant distance so that we're using different formulas and expanding on that knowledge of the E field formulas that we were given for a perpendicular and parallel dipole moment. And we could also start by including the dipole moment and work backwards to find E negative field such that E net is 0 at the origin. So you can start with a different portion that you understand, and then if you work to solve it and you're getting the same answer, then you did it correctly. So this is our review of question 1 on dipole moments, and thank you for listening.